Hello everyone, here is lecture 5 on solid electronic materials. In this lecture we have to discuss on density of states, occupation probability, Fermi level. There is kind appeal for ignorance of alignments. In band theory, we have seen that if there are n energy levels in a band, then there will be 2n energy states and each state will be filled by a single electron. So density of states represents two empty states and the electron distribution function represents two states filled by electrons. Let us see. The number of energy states per unit volume, per unit energy range, okay, is called density of states. That is expressed by G. So number of energy states per unit volume, per unit energy, okay, is called density of states. That is expressed by 4 pi by h cube to the power 3 by 2 e power 1 by 2. If we talk about the density of states in the energy range D, then D is multiplied. According to the need, we have to multiply here to how much range we have to discuss the density of states. Okay, so left side represents to the density of states in D energy range. If you draw a curve between density of states, which is a function of E, and energy, then we have a parabolic curve. By reducing energy, okay, density of states gradually reduces. See, and when energy becomes 0, then G also becomes 0. So let's see if an empty state is filled by electron, then how that will be converted into electron distribution function. If you have the probability Fe for an energy level E to be filled by an electron, okay, energy state, okay, of energy E to be filled by electron, okay, probability. Then by multiplying this one with the density of states, okay, we have electron distribution function. Means it represents how electrons are distributed in energy states. Okay, here Ne represents to per unit energy. If you talk about D energy range, then it represents to number of electrons, okay, filled in state in the energy range D. In other words, Ne represents to carrier distribution function or electron distribution function. So how electrons are distributed. So density of state is multiplied by probability. This probability represents to an energy state E filled by an electron, single energy state. And if this is multiplied with the number of energy states, okay, so we have the number of electrons, and by multiplying energy range, we have the total number of electrons in the energy range D. Okay, since this term is a function of E, because of it is expressed as function, distribution function. Let us discuss furthermore on Fe. As we have already said that it represents to the an energy level or energy state E is filled by electron is called probability distribution. In other words, it is given by Fermi-Dirac. Because of it is called Fermi-Dirac distribution function. Distribution word is used because how electrons are distributed in energy states. Okay, it represents to that one because of it is called Fermi-Dirac distribution function. It is expressed by this one, where EF represents the Fermi energy and K is the Boltzmann constant. If energy states are completely filled, okay, then it will be, since it represents the probability to fill by any energy state of energy capital E, so it will be, if states are filled, means it must be 1. If states are empty, means they are not filled, so it will be 0. So let's discuss on this point. Now let's discuss on Fermi level. If you talk about 0 Kelvin, 0 degree Kelvin, okay, see this figure. All energy levels is an energy level, not state, since a level is filled by 2 electrons. If it is a state, then there can only be a single electron. So energy levels are filled by 2 electrons till an energy level, till an upper energy level, which is called Fermi energy. Okay, at 0 Kelvin. So Fermi energy level is that level till to that electrons are filled. Okay, and then upper energy levels are empty. In other words, if we correlate the filling of electrons in energy levels with the probability function. See, if you draw a curve between energy and probability distribution function, so by increasing energy, see, by increasing energy till 2 all states are filled, and that means all levels are filled by 2 electrons. A level is divided into 2 states, so a single state will also be filled by single electron. So all states as well as all levels are filled by electrons, so probability distribution function will be 1. To see here, by increasing energy, Fe is 1 till to Ef. When E becomes Ef, okay, and then afterwards there are no electrons. So till to Ef, okay, E equal to Ef, Fe equal to 1. Okay, and then afterwards there is no electron, because of it suddenly reduces to 0. Fe reduces to 0. It shows the variation of distribution function with energy. So it is 1 means completely filled. Energy states are completely filled by electrons. Because of this distribution function is 1, approximately 1. And as soon as it reached to Ef, it becomes 0. Similarly, by discussing on the number of electrons, we can see number of electrons are increased. See, number of electrons are increased. First of all, there were 2 and 4, 6, 8, 10. So number of electrons are increased into energy here. Then after 0. So increased. See, afterwards there are no electrons, so it becomes. Okay. So this curve represents to the variation of charge carrier distribution function with energy. So Fermi energy is the highest occupied energy level at 0 degree. Let's discuss on few cases. If energy of electrons below Ef is E, okay, then less than E. Okay. Now, if you talk about that 0 Kelvin, see, according to this one, T is 0. So 1 by 0. Okay, T is 0. And if E less than Ef, okay, so exponential will be, if there is 1 by 0 means infinite, and E less than Ef means minus infinite. So here will be e power minus infinite. Minus infinite means 1 by e power infinite means 0. Okay. So here will be 1 upon 1 will be 0. Here by mistake it is printed as 2, but here will be the 1. So 1 is 1, and here 1 by e power infinite means 0. So Fe equal to 1 means below levels, okay, are completely filled by electrons. The levels below than Fermi energy are completely filled by electrons. So because of probability distribution function is 1. If E is greater than Ef, we'll see. If E greater than Ef at T equal to 0. So E greater than Ef means T is 0 means 1 by infinite, and E greater than means plus infinite. So plus infinite. E power infinite means infinite. So infinite. So 1 by infinite means 0. So upper energy levels, we have already been seen that upper energy levels are empty. So probability of to be filled by electrons will also be 0. Now what will happen if E equal to EF at T is equal to 0? See, T is equal to 0, E minus EF 0. So E power 0 upon 0. 0 upon 0. It can't be calculated. So it may be in between 0 and 1. We're talking about T equal to EF. So these points are discussed at T equal to 0 Kelvin. Let's see at higher temperature what will happen. At higher temperature means this term T will not be 0. Now depending on this one, that can be discussed. So it will not be 0. Now talking about the temperatures greater than 0 Kelvin. Thermal energy is provided. We know that that is expressed by kT, which is equal to 0.026 electron. Okay. By acquiring this energy, the electrons residing in EF, okay, will shift to the energy level, will shift to an energy level of energy is equal to EF plus kT. And electron lying just below the EF will shift to the energy level just lying below the top one electron, this one. And similarly, the bottom third of Fermi level will occupy the bottom third of top electron. So, by gaining this thermal energy, the energy levels below to EF are partially become empty, and uppers level in the energy range of kT, okay, are partially filled. There is a change in the distribution of electrons in the range upper kT and lower kT, okay, energy values. It can also be seen in the Fermi distribution function. Since here the probability distribution function till to EF is little reduced than 1. So see, by increasing the energy, so till to this level, Fermi energy distribution function is 1. So see, Fe is 1 till to this level. So that is 1 till to this level. And afterwards, single electrons are jumping toward the upper vacant levels because of probability is little reduced. So probability is little reduced till to Fermi energy. And then afterwards, previously there were no electrons, but after gaining energy, few electrons are jumped there. So there is also some amount of probability. So here, so upper level of energy level, okay, we have the finding probability. Okay, see, till to upper filled electron, and then afterwards it becomes 0. But till to upper electron level, okay, we have the probability. The same thing can also be seen in the electron distribution function. So electrons are increased till to this level, but afterwards, due to jumping, few electrons are reduced here. So few electrons are reduced here, and few electrons are also obtained in the upper level. So few electrons are also obtained in the upper level. So there is a distortion in the electron distribution function as well as in the probability distribution function. Okay, at temperatures greater than 0 degree Kelvin. Let's see. So what is the value of probability distribution function at high temperatures? If T is greater than 0 Kelvin, okay, and E equal to EF. Here T greater than 0 and E equal to EF. E equal to EF. So E power 0. E power 0 means 1. E power 0 means 1. At E equal to EF. So 1 by 2. So F equal to 1 by 2 or 0.5. So Fermi energy level is that level till the probability distribution function is half or 0.5. In other words, the probability of electrons to be filled till to Fermi level is 50%. Okay. it will be maintained at all temperatures. So see, at 0 Kelvin, the Fermi level means the topmost energy level, till 2 electrons are filled. But here, at different values of temperature, Fermi energy is that level till 2, the probability of electrons to be filled is around 50%. Okay, or its value is 0.5. So this is called Fermi energy. In other words, it is also called the average energy of electrons at all temperatures. Fermi energy means average energy of electrons or charged ions. See, in this curve, small amount of temperature is provided. So till to this one, electrons are affected. So there is change, little distortion is here. This one. If temperature is higher, then in-depth electrons will also be affected. As a result, okay, there is a distortion is here. By increasing further, then the deeper electrons will also be affected and jump to the higher levels. Okay, the previous one we have discussed. By increasing the temperature, this effect will be observed in the lower levels also, and these electrons will jump to the higher levels. As a result, it will be turned soon than this point. Okay, it will be turned from here, depending on the temperature. It will also be turned soon. By increasing the temperature, deeper electrons will also be affected. As a result of that, this kind of curves are obtained. That's all in this topic. Thank you.